So now we have seen what is the definition of modular exponentiation and a couple of simple ways to implement it. And in the next couple of slides, I'm going to show you 2 examples on how it can be applied for modern cryptography. And I'm sure that Professor Jonathan Katz has showed you more examples about this in his course on cryptography. The first example is on the Diffie-Hellman key exchange. In this case, there are 2 people, Alice and Bob. They want to talk to each other, but they want their message to be encrypted. So in that way, they want to share the same key. So what Alice is going to do is she's going to find a random number x sub a, and then she's going to raise a base a to the power x sub a and doing the modular q operation. And she's going to call this one y sub a. What Alice is going to do is she's going to send y sub a to Bob, the partner she's going to talk with, and then meanwhile keep x sub a as a secret for herself. On the other side, Bob is going to do exactly the same, and which I highlight everything into green, just trying to distinguish what Bob is doing compared to what Alice is doing. So Bob gets x sub b, and then raise a to the power of x sub b, and call this result y sub b. And he's going to send y sub b to Alice, and then keep x sub b as a secret for himself. Now, Alice has Bob's y sub b, and she has his own x sub a. So how Alice is going to generate the shared key here. So here is the key generation protocol. So what Alice is going to do is she's going to raise y sub b, which is the message coming from Bob, to the power x sub a, which is the secret she keeps for herself. And then doing these things under the mod operation. And on the other side, Bob is going to do the same. And why this gives them the same key, shared key? This is the underlying math for this one to be true here. So from Alice's side, what she calculated is a to the power x sub b, which is this y sub b, raised to the power x sub a. And then from Bob's side, what he has computed is y sub a to x sub b. And where y sub a is actually a to the x sub a, as I raised to the power x sub b. So what you see here is for this inequality on the left-hand side, you have a to the power x sub a, b times x sub a. On the right side, you have a to the x sub a, and then x sub b. And we know these two actually, they are the same. So that is the reason in this way how they can share the same key here. So however, we realize in this protocol, both Alice and Bob, they have to do this modular exponentiation many, many times. Here, here, and here. Both for them to generate the message to send to each other and also trying to generate the key. So this is a very, very critical operation for both parties. And the second example we're going to show is a public key encryption scheme called RSA, which is named under its 3 inventors. So this is an asymmetric encryption scheme, which means the encryption key and the decryption key, they're different. So in this protocol, what each user has is a pair of keys, a public key and a private key. So one user wants to do an encryption. So for example, I want to send a message to a certain user, let's say Bob, who has this pair of keys. So what I'm going to do is I'm going to encrypt the message using Bob's public key, which everybody knows. And then this message comes from P, becomes encrypted, becomes the ciphertext C here. When Bob receives this ciphertext C, he will be able to decrypt it using his private key and the decryption algorithm. So he decrypted the ciphertext C and then get the message, the plaintext P back. For this protocol to work, we need the following requirement here. For the same message P, after I encrypted it using Bob's public key, and then after Bob decrypted it using his private key, this message should remain the same. So that is the underlying protocol for this RSA public key encryption. So currently, the key size for RSA is about 10,024. but very soon it's going to be doubled or even, quadrupled. So let's see what is the encryption and the decryption algorithms, what schemes RSA is using here. So in RSA algorithm, what users is going to do here is going to select two prime numbers, P and Q, and then they're going to multiply these two prime numbers. And then they're going to choose a small number, or maybe not that small, smaller than n for sure. So it's a number E which is relatively prime to P minus 1 times Q minus 1. And the next step is a little bit of challenge. So what you need to do is you need to find another integer D such that E times D is equal to 1 mod P minus 1 times Q minus 1. Okay? And once this is done, the user will have a pair of public key and private key. And with this public key and private key pair, we can do encryptions, we can do decryptions. Okay? And what you realize in this case, the encryption function is a modular exponentiation. The decryption function, again, it is a modular exponentiation. And why it works in this case? So we see what happens here is, so if I have a message X, I do the encryption, and then I do the decryption. And from the fact, from number theory, we know that when X raised to the power E times D, and as long as this E times D mod P minus 1 times Q minus 1 equal to 1, and then this X to the power E minus D mod N equal to X, which means you can get the original message back. So again, from this example, we see that we need to calculate modular exponentiation. We need to compute modular exponentiation. So next, we're going to show how we can compute this one efficiently. So this is another small example to show how this works in real time. So we select P equal to 11, Q equal to 17. These are two prime numbers. And then following the definition, N is the product of these two, which is 187. And then P minus 1, which is 10, Q minus 1, which is 16. So their product will be 160. I choose 7, which is relatively prime to 160. And then I find out 23 is the magic number. That's 7 times 23 mod 160 is 1. So this will be my public key, and this will be my private key. So now, if I want to do an encryption, I want to encrypt the message X equal to 88. All I need to do is I raise X to the 88 to the power 7, which is the public key. Okay? And then this gives me, when I do the mod 187, give me the ciphertext 11. So I'm going to send this message 11 to whoever is the receiver, who has this 7 as the public key. So when this person receives the ciphertext y equal to 11, he or she is going to raise this to the power of the private key 23. And then do this modular exponentiation operation, and then find out the message is 88. So now the question remains is, how do we compute 88 to the power 7 or 11 to the power 23 mod 187? And in general, when RSA has a large key size of 1,000 bits or maybe 2,048 bits, how can we compute this modular exponentiation efficiently?